Yo, all right, we're back here. Continue with slope fields. Let's take a look at the differential equation dy dx equals 2 times y. All right, so you've been asked to write or create a slope field for that differential equation. So how do we do it? Pretty simple. It's basically just plotting points. So you go point by point on this little grid. Did a little bit nicer job here making that grid. Thank you very much. So let's look at this point here, 0, 0. So 0, 0, remember that's the x, that's the y. Plug this into this differential equation. So if you think about it, you're only plugging the y in because there's no x in it. So 2 times 0 is 0. So you draw a short line segment indicating a slope of 0 like that. All right, and then you're just going to kind of go through it. So then maybe I'll go to this point here, which would be the point 0, 1, right? So plug that point into this differential equation. Evaluate the derivative at that point, right? It's going to be 2 times the y value is 1. It's going to be 2 times 1 is 2. So, all right, that means I have to go up 2, which I don't see the grid up here, right? So up 2 over 1. So like that's where the point would be. That's where I'm aiming. So that's a short line segment indicating a slope of 2. And what you may have noticed here is this is different than the ones we did in the last video, in which that vertically they were all the same. Well, that should make sense to you because this differential equation now is in terms of y, not just x. So when it was in terms of x, then vertically everyone's got the same x value. Yeah, the slopes are the same. But when it's in terms of y, all the y values are going to be different now, right? I didn't label these grid points. I probably should have. That's 1, that's 2. -1, -2, 1, 2, 1, -2, right? So let's kind of go through this a little bit more here. So like right here at the point 0, 2, right? Again, there's my x, there's my y. 2 times 2 is 4. So I got to go up 4 over 1, right? Or if I wanted to be super clever, I can go left 1 down 1, 2, 3, 4. So I'm kind of aiming for that point down there, right? So it should be steeper. Okay, so there's my slope of 4. There's my slope of 2. Here's my slope of 0. At this guy here, the y value is -1. I don't really need to keep writing these points out, right? I know the y value is -1, so I have to do a slope of -2, right? Because 2 times -1. So that's down 2 over 1. So I'm kind of aiming right there. And then this guy, that was actually bad. All right, so yeah, let me go back to that. That looked like a slope of -1. I want a slope of -2. All right, and then this would be a slope of -4. So it's not an exact science, but you should do your best to make it look good. So again, notice they're all different here. So is there anything that's going to happen when your differential equation is just in terms of y? So in other words, when it was just in terms of x, vertically they look the same. If it's just in terms of y, is there anything special that's going to happen? All right, this is when I'd give you a couple of seconds and ask you to talk to your partner and see what's going on. All right, so we're back. Davis, what do you think? Anything going to happen? Yes, Davis, you are correct, right? Horizontally, they're all going to look the same. And think about why that makes sense, right? If I look at any of these points that I'm dotting right now, they all have different x values, but they all have the same y value. And what is that y value? It's 0. So 2 times 0 is 0. So from left to right, all of these slopes would be the same. Same thing here. If you look at any of these points that I'm dotting right now, they all have different x values, but their y values are all the same, right? So their y values are all 1. So all of these are going to have a slope of 2. So they're all going to look the same. Likewise, these would all be slopes of 4. These would all be slopes of -2. And these would all be slopes of -4. All right, and there is your slope field. So this is the slope field for the differential equation dy dx equals 2y. What is it again? Remember from the last video, this is a visual for you to see the general solution. In other words, you're seeing a family of functions here, or maybe relations, differing by a constant that satisfy this differential equation. All right, now sometimes when you do it by hand, it's a little bit annoying, so we'll rely on technology, which on one of your homework tonight, I'm going to want you to do that as a check. So let's go back to that guy. So that was GeoGebra. I'll give you the link for that. In GeoGebra, you can actually put in your grid values here, right? So your x min, that's the x to the left, your x max, x to the right, y min, y max. All right, if I wanted this to look like what I just did, and I'm going to want you to do this on your homework when you follow the directions, right? I went from -2 to 2 on the x and -2 to 2 on the y. So we can actually make GeoGebra do that for us. So take a look here. Let's just go ahead and chuck in -2 here, 2 there, and then on the y, same thing. And it kind of gives you the grid that you're looking at. Now, what's a little interesting here is you sometimes have to mess with the density, right? So obviously that doesn't look like the slope field we just made, right? Because we made slopes at each individual whole number x value. And you got to kind of play with it until you get it. So you see how, bam, I just got it. So I kind of moved my density little slider here to the left, and now I see slopes drawn at each grid value. All right, so that's how you can check the work you have done. Right now, obviously, this isn't the greatest. If we really want to get a good idea of what's going on here, I'm probably, not to check my work here, but I'm probably going to make this a little bit bigger just for note flavor, or I should say video flavor now, right? And then increase the density. And so now you can get a pretty good idea of what those family of functions differing by a constant look like. So if I was to ask you, say, hey, and I'm going to do this on your homework, go ahead and plot the point to -1. I might ask you to plot a different point and then sketch the curve in. So you go over to 2, -1 and then sketch it in. Would you be able to do that? Well, if you were seeing this, then yeah, you'd be good. All right, so this green curve is a particular solution that satisfies not only the differential equation, but the point to -1. All right, I'll show you some other examples. This is going through the point -0.8, comma, -3.38. All right, different point. That's a different point. That's a different point. Notice when you come up here, you get that going on. So take a look at these functions. What do they look like to you? And do you see maybe something that's happening at the x-axis? So let's go back to our differential equation here. Let's do what we've been doing, which is solve this. All right, so here we go. So if I'm going to solve this differential equation again, right, I have my dy up top on the left. That dictates that the y's are going to go over there. So divide both sides by y and then multiply both sides by dx. So the variables are separated. Okay, so I have 1 over y times dy equals 2 times dx. You need that times, right? It needs to be in a Riemann integrable form. This gives me the green light to integrate both the left and the right. Do I know a function whose derivative is 1 over y? Absolutely. It's ln absolute value of y. Integral of 2 is just going to be 2x. If I left it like this, as you know by now, you would get hammered by the AP people who grade your test because you forgot the constant of integration. All right, I'm going to solve this for y. That's why, by the way, I put the c over there, by exponentiating both sides. E to the ln of absolute value of y is just absolute value of y, right? These are inverse functions. They undo each other. And then here I get e to this side. That's what you get, okay? So remember the little trick that we did here, right? A little exponent rule you learned in 7th grade. I can rewrite this as e to the 2x times e to the c. Remember that little rule of exponents? When you multiply two terms with the same base, you add the exponents. You're just doing that in reverse. And so now if you think about it, e to the c, that's just representative of a constant. So I'll change e to the c to k, representing any constant. And now since I'm putting k times e to the 2x, I can choose x's and y's that will decide whether or not k will be positive or negative. So if that's the case, then I don't really need these absolute value bars anymore. So I'm going to lose them. So this is what I get. So this is my family of functions differing by a constant. Okay, so you're like, oh, exponentials. That's kind of looks like what we got over there before. Now, if I made this initial value problem and said, find the particular solution that goes through 2, -1, so -1 equals k times e to the 2 times 2, right? So it probably would have been cooler if I did 0 something, because this would have got the e out of it, but whatever, it doesn't matter. So now that's just e to the 4th. So I'm going to get -1 over e to the 4th. That's just a number. That's my constant. And so y equals -1 over e to the 4th. That's just a negative number, right? Whatever it is. times e to the 2x. This would be my particular solution. So this is the general solution, right, which we see when we look at the slope field and we see the whole thing like this. And then this is the particular solution. So this specifically goes through the point, see if we can get green here. Oh yeah, 2, -1. So if I came over to 2, -1, I didn't draw the a very comprehensive guy here, and now I said, hey, sketch in your particular solution. Well, these are flat slopes here, so that kind of indicates to me that I'm not passing that. All right, so that means that that's probably going to be, what do you think? You guess it, an asymptote there. So this would be the particular solution, y equals -1 over e to the 4, e to the 2x. Okay, so the red represents your visual of your general solution, and the green represents your particular solution. So hopefully you're starting to see that, all right? And depending on where you pick the point to start, if I pick the point up here, let's just for kicks and giggles do this. Maybe I want you to sketch in the particular solution that goes through 0, 1, right? So if I did that, now again, horizontal line here, right, I'm going to get that, which again, these look like exponential functions. This is a negative exponential. This is a positive exponential. And as you know, exponentials have asymptotes, horizontal asymptotes. In this case, it would be at y equals 0 or the x-axis. So this would be the particular solution that goes through the point 0, 1, which I did not find the equation of that, but if I wanted to, I can just do 0, 1, plug it in, solve for k, and I would get it. Okay? So not so bad. So you're going to be asked to do that on your homework. Create the slope field. You can check it in GeoGebra and then sketch in a particular solution. And then after you sketch it in, go ahead and then find out what it is for real and see if it seems to jive, if it matches up. All right? Cool beans? All right, let's move on. Let's do one more. All right? Let's do, let's see here. Let's move this down a tad bit. Like that. Let's do dy dx equals x times y. All right, this one's going to take a little bit longer. All right, so what's the story here? All right, well, now what you got going on is you have a differential equation, right, that is both in terms of x and y. So when I go to plot the slopes now, right, to get a visual of what the general solution might look like, let's take this point here, 0, 0, right? So if I plug 0 in for x and 0 in for y, I get 0. If I go up, this is the point 0, 1. So that would be 0 plus 1. That would be a slope of 1. Aim for that. Bam. If I go over, this would be the point 1, 0, right? 1 plus 0, that's a slope of 1. I'm aiming there. If I go to this point here, I'm just jumping around, right? This is 0, 2. So that's going to be 0 plus 2. That's up 2 over 1. So that would look like that, a little bit steeper. And the idea here is that it's going to be different for every grid point because there's an x and a y in it, which is kind of annoying. All right. So, all right, I'm going to give you a second here to complete this on your own, and you really should. So take a second and pause and go ahead and fill in the rest of these right here. All right. All right, so hopefully you hit pause and you did it. What I'm going to do now, and this is what I would expect you to do on your homework, so I'm kind of like demonstrating it, is you would check your homework by going over to the GeoGebra link that I will provide in the calendar, putting in the slope field equation right here, which is x plus y, putting your grid in, and I forget the grid that I'm going to give you for your homework, but if we're following what I'm doing right here, it looks like I did -3 to 3, actually, no, -2 to 2 in every direction, right? So let's go back here and let's go and change that. So -2, 2, -2 to 2. And what's going to happen is at first glance, right? And let's shut all these particular solutions off. At first glance, right? When you have this going on here, obviously this is a lot more slopes drawn here because of the density. So you got to kind of move this slider and get it to where you see that the slopes, bam, there it is, are drawn at your grid points. And that's what your slope field should look like. So whatever you just created should look like that. So it's a real good way to check it out. So hopefully you can do that. All right, so now again, but for visual purposes, if we were like wanted to really see what those family of functions look like, maybe I make my grid a little bit bigger. I'll go back to -5 to 5. And that's not the greatest, right? So how do we make it better? We increase the density, and you can kind of see by sliding this around a little bit what the family of functions would look like here. So again, if I drew a solution curve through 2, -1, this point right here, what's it going to look like? Right? And kind of like follows this stream. So bam, that's what it would look like. What if I picked a point over here, right? What would it look like? It's not going to mirror this. It has to follow the slopes, right? It's almost like a stream or a current. That's what that solution curve would look like. Okay, so again, the green guys are the particular solutions that go through or satisfy a certain point, whereas the black slopes there, that's the overall visual of what the general solution looks like. In other words, the family of functions. All right, so now let's kind of do what we did with the other question is, well, let's find it. Let's solve it, okay? So if I go ahead and try and solve this thing, you're like, all right, we could do this. So let me rewrite it. dy dx equals x plus y. So according to me, the dy is up top over here. So that means the y's have to go to this side. So how do I move this y over, right? You're like, well, it's plus y. And by the way, that's bad. You're like, why? Well, let's find out. So to get this y over, you would have to subtract it from both sides. Look at me showing the little 8th grade work here. So if I did that, I'd get, and I'll kind of write it over here, dy dx minus y equals x, right? And honestly, what I probably should have did is, and maybe I can do it now, like I'm going to stop. You stop right now, stop the video and try and do this. Try and separate the variables. It's actually a pretty good exercise. See if you can get the y's and the x's separated and in a Riemann integrable form. All right, so hit pause right now. Okay, so you're back. How'd you do? Hopefully you didn't wait too long. You didn't try too long because it may have ruined your whole day. So anyway, back to here. So like, all right, I got my y's on the left side. I got to get rid of that dx. So how do I do that? Well, the only way to get rid of divided by x is to multiply both sides by dx. You have to multiply this side by dx, and you have to multiply this side by dx. So if I do that, you're like, well, wait a minute. Here it cancels, but then it's just going to come in right there. So that's quite annoying. And then here it looks good. So the right side's Riemann integrable, but the left side is not. It's a mess. So this didn't work. So this idea of subtracting y over, did not work. So hopefully you didn't suggest this, but maybe someone said, hey, why not instead of subtracting y, do what we normally do, which is divide by y. You could do that, but remember, you have to divide the entire sides by we're doing, quality of operations here when you're working with the equation. So, all right, you want to divide this by y, you got to divide that by y too. And you got to divide that by y. And so now I'm going to get 1 over y dy dx equals x over y plus 1. So it made that 1, but you still have a y here. And now if you multiply both sides by dx, right, you're going to get 1 over y dy when you multiply this side by dx. And maybe I'll continue to show the kitty work here. So wablam, and then wablam. And so now, all right, here it cancels, but here you get x over y dx and then plus dx because multiplication is distributive and the left side's good, but now the right side's a mess. So long story short, guys, you can't solve this with separation of variables. It is impossible. And we have alluded to that before. That separation of variables is a limited solving technique. And an equation, when you think about it, a differential equation as simple as just x plus y, it can't be solved with this method. So then that should make you think, well, then slope fields are kind of powerful, right? Because I can't solve that differential equation, right? But I can certainly make a slope field for it because if you know how to plot points and sketch slopes, right? then you can make a slope field. So even though I'm not able to solve the differential equation, I can get a pretty good visual of what those family of functions are going to look like. And that's kind of like the whole point of a slope field. So it's kind of neat when you think about it. All right, so your homework, I'm only giving you one homework question tonight. It's actually written on a calendar, so you can get it from there. It's one differential equation where I want you to first make a slope field, then I want you to solve it. It will be solvable. Then I want you to sketch in a particular solution through a point, which I'm going to say about 50% of you are going to get correct and 50% are going to get wrong, and we'll talk about it when I post the solution video to it. And then the final thing would be to find that particular solution, and that might actually make you correct your sketch. We shall see. So good luck. Crush it. Hope everyone's safe. Peace out, Cub Scout.